Okay, so residence time. So imagine you wanted to dye your dog. Okay, so I don't recommend that this is a thing that you should do. But if you wanted to dye your dog, you wanted to mix up the dye properly. Okay, and get it to the right colour before you dip your dog in it. So don't dye your dog or anybody else's dog. So this is just an analogy for mixing times and more specifically for residence times in the ocean. Okay, or actually residence times in any component of the Earth system. Okay, so imagine you had a bucket of water and you had some dye that you're going to put into that water. Okay, so initially there's no dye in the water. So although there's lots of water in the bucket, the content of the reservoir of dye, which would be the bucket. The dye in the bucket, not the dye in the beaker, that's zero. So we start by adding, say, a flux of dye. So we start pouring in, and over time, the content of our reservoir or our bucket here, that starts to increase. Okay, and at the moment we've got quite a low concentration of dye in the bucket. Okay, so the concentration times the volume, so the total amount of dye in the bucket is small compared to the amount of dye that we're adding, or the rate of dye we're adding. Okay, so if we add some dye, the concentration of the bucket will change, and it will change quite readily, and it can do that because the amount of dye that's already in the bucket is relatively small compared to the amount of dye that we're adding. So if we were to, for instance, if we were to then maybe add more concentrated dye, okay, because the concentration of the dye in the bucket is very low, so the total content of dye in the bucket is low, if we were to add more, if we were to increase the flux of dye into the bucket, then the concentration will respond relatively quickly. Okay, so in this is an analogy of basically the residence time of dye in the bucket is quite short, so changes in the flux of dye into the bucket will change the concentration. Okay, but once we've got to a situation like this where maybe we've got lots and lots of dye in our bucket, okay, if we were to reduce the flux, or we were to start pouring in a lower concentration dye or something like that, okay, because the amount of dye in the bucket is now very large, by changing the flux into the bucket, okay, we're not going to be able to change the concentration so readily. It will change, but it'll be a small percentage of the amount of dye that's already in the bucket. Okay, so even if we were to increase the flux again, okay, it's still not going to have a big effect on the concentration. In this case, this is because it's an analogy that the residence time of the dye in the bucket is large. Okay, so there's a large amount of dye in the bucket relative to the amount that we're adding, or the flux that we're adding. So that means that the rates of change of the concentration of the buckets will be relatively slow. Okay, so one of the things with residence time is that if you have a very short residence time, it's very easy for the total content or concentration of something in that, or of the thing that the residence time refers to, in that bucket is able to change quite quickly. Whereas if you've got a very long residence time, okay, so if you've got a very high concentration or amount of stuff in your reservoir, if you change the flux a little bit, okay, it won't have a big impact on the concentration or amount of stuff in your reservoir because the residence time is long, you've got a large amount of stuff there, and you're only changing the fluxes by a relatively small amount. Okay, so you can think of as the residence time as the kind of ratio of amount of stuff in your reservoir, in this case the amount of dye in your bucket, relative to the rate of dye that you're adding. Okay, or relative to the rate of the rate of dye that you're adding. Okay, so to think about this in terms a little bit more mathematical and a little bit more rigorously, so systems in the Earth are not as simple as a bucket of dye. Okay, so we have a flux in, and we quite often have an output flux. Otherwise, our reservoir would continually accumulate matter. Okay, so let's just think about what this kind of means. If we just imagine this box that we've got in the middle here, if we imagine this box is the ocean, okay, and we can think about maybe the residence time of water in the ocean. Okay, so this is, we have an input flux. Okay, we have an input of water into the ocean by rain and by rivers. Okay, and that might be in kind of kilograms per year. Okay, amount of water coming into the ocean. And we have a total volume of the ocean. Okay, and the total volume of the ocean is very big. Don't need to worry about that for the moment. And we also have an output flux. So if the total amount of water in the ocean is to stay constant, and we kind of think that's kind of true over quite long time scales, the flux in should equal the flux out. And in this case, the flux out would be the evaporative flux, so evaporation of water from the surface. So what we can do is we can calculate a parameter called the residence time. And the residence time is simply this equation here. So this is the symbol for, it's a Greek letter tau. Sometimes you get a T with a subscript res for residence time. And it's the mass of the reservoir, okay, divided by one of the fluxes. Okay? And this makes the assumption that the system is steady state. So the total mass of the reservoir is not changing, which means the input flux must equal the output flux. So if we then work through the units, so if we've got maybe the total mass of the reservoir, that might be in, say, kilograms, or it might be the total amount of stuff in the reservoir, which might be in moles. Okay, so that would be, say, mass or moles divided by the flux, and if you had a flux in mass, the reservoir in mass, the flux must be in mass per time, so kilograms per year or moles per year if you were thinking about the reservoir in terms of moles of reservoir. So if you work through the units there, that would be kilograms divided by kilograms per year. Okay, so that gives you the units of the residence time. That's kind of a units of years. So okay, that works out quite nicely in terms of just working our units through an equation that it makes sense. So what does that mean, this residence time? Okay, so what you can think of it as the average amount of time any one molecule of water, okay, spends in the reservoir. Okay, so it gets inputted, okay, and then it spends some time in the reservoir, and then it gets outputted. Now, some water might come straight in and straight out again. Some of it might kind of sit around in the reservoir for some time before eventually being evaporated out. But the average amount of time any particle spends in the reservoir is the residence time. And okay, you can think of this through and imagine if you had a very short residence time. So you can imagine if you had a very small reservoir and very large fluxes, it wouldn't take very long for the system to kind of completely flush through. It wouldn't take very long for a particle to work its way through from input to output. Okay. Another way of thinking about what the residence time would be, okay, rather than the average time a particle or a molecule of water would spend in the reservoir, is the amount of time it would take to halve the mass of the reservoir if you removed the input flux and kept the output flux constant. Okay, so you can imagine if you stopped all rivers, okay, and kept evaporation kind of going, then the mass of the reservoir would decrease through time. Okay, so if we stopped this flux here, if we stopped that, okay, but kept this one going out and somehow magicked all of the water away and stopped it getting back into the ocean once it's evaporated, okay, the size of this reservoir would decrease down over time, okay, as we progressively remove the water. Now, the amount of time that it would take to remove half of the water, okay, is the residence time. Okay, so you can think of it as a residence time as also a measure of how long it takes to change the amount of stuff in the reservoir. Okay, and in this case, we're thinking about mass of the ocean, but also kind of more usefully, we don't have to think about the mass of water. This concept also works for dissolved concentrations of stuff in the water. Okay, so in the case, you might think of, say, maybe an element like calcium. So calcium is dissolved in river water, and that makes its way into the ocean, where it stays dissolved. And then it has an output flux. Okay, so calcium is removed from the ocean by the formation of things like shells or coral reefs. These are things that produce calcium carbonate shells, and that removes the calcium from the ocean. Okay, so rather than thinking about the total amount of water, we can think about the total flux in terms of number of moles of calcium coming in the river, okay, which would be the concentration of calcium times the flux of water, okay. And we can think about the total amount of calcium dissolved in the ocean, and that would be the concentration of calcium times the mass of water, okay. So it's kind of similar to think about the water, but you just need to think about the dissolved phases as well, okay. So just to recap, that the mean residence time of anything, whether it's a dissolved component or the water itself, okay, is we think of the total amount of stuff, okay, whether it's the total amount of water, or in the case if we wanted the residence time of a particular element dissolved in that water, it would be the total mass of that element in the whole reservoir. Okay, so the mass of the reservoir in terms of how much water there is times the concentration, divided by the flux. Okay, so this would be the input flux or the output flux. Okay, in the terms of calcium, it would be in the moles of calcium added in rivers per year, or the moles of calcium being produced in terms of shells per year. And importantly, we make the assumption that the total amount of calcium is staying constant in the ocean. So the input flux is equal to the output flux. Okay, so we can work through kind of a few little examples of that. So if we just consider water, so we're looking for the residence time at the top here of water in the ocean. Okay, so the amount of water coming into the ocean is this number at the bottom here. The amount added from rivers is the flux. The total amount of water in the ocean, this is our M, this is our S. Okay, so we've got a number 1.37 times 10 to the 21 kilograms of water in the ocean, which is a huge amount of water. Very, very large is the ocean. And you can look up and find out from a database of river kind of discharges how much water flows into the ocean from rivers each year. Okay, so we're making an assumption here that all of the water going into the ocean is from rivers. Okay, so this flux might actually be a bit larger if we consider rain that falls directly into the ocean. But either way, just to get an approximate figure, we've got this number, which is the total mass, divided by the flux. Okay, so we get an answer that's kind of 40,000 years. And this is probably a little bit of an overestimate, because if we make this number here bigger and include kind of the rain flux directly into the ocean, okay, then this might come down to maybe 20,000 years, something like that. Okay, so in this case, we've got a residence time for water in the ocean of 40,000 years. So what that means is that kind of the average water molecule, once it enters the ocean, kind of kicks around in the ocean for about 40,000 years before it's removed by evaporation again. Or if we were to, for instance, stop all of the rivers flowing into the ocean and magically not allow the evaporated water back, then it would take about 40,000 years for the oceans to kind of half go away. Okay, which is massively unrealistic, because that's kind of never going to happen. But just to say that if that were to happen, you could imagine geologically it could happen kind of relatively quickly. Okay. So the next thing is to maybe look at something else that's dissolved in the water. So we could look at the amount of chlorine in the ocean. What's the residence time of chlorine? Okay, so then we need to work out, rather than the total amount of water, we need the total amount of chlorine dissolved in the ocean here, okay, and the total amount added each year in rivers. Okay, so we've got some information here. We've got the seawater concentration, it's about 1.9% chlorine. Okay, so that's because the ocean is quite salty, so sodium chloride makes up most of salt. So 1.9% of the water is chloride ions. Okay, so to work out the total mass of chlorine in the ocean, we take the concentration, the amount of water down here, and we times it by the concentration. So times by 0.0194, something like that. Okay, so this gives us the total amount of chlorine in the ocean. And river water is much less kind of much less salty. So it's got hardly any dissolved ions in it, really. So it's kind of tastes quite fresh. Doesn't have not so salty. So typical river water might have 5 milligrams per litre. Okay, so there's 1,000 grams in a litre, there's 1,000 milligrams in a gram, so this is 5 million kind of times smaller than the amount of water. So we can think of that as 5 parts per million, which is what we have down here. So 5 times, or 5 basically divided by a million, 5 millionths of water is chlorine. So once again, we times our river flux by the concentration, okay, to get the total amount of chlorine added each year in rivers, and we work through that maths and we get an answer that's 150 million years. Okay, so that implies that the concentration or the amount of chlorine in the ocean it doesn't really change much. It has a very, very long residence time. So if we were to massively increase the river flux of chlorine or massively reduce it, it wouldn't change. It would take an extremely long time for it to have any effect on the concentration of chlorine in the ocean. Okay, so we can just quickly to kind of recap, this is the kind of where, or some of the concentrations or compositions of stuff in the ocean. So most of the ocean is made up of oxygen and hydrogen, okay, because that's the elements that make up the water molecule. And then the other kind of large concentrations are from chlorine, sodium, magnesium, calcium, potassium, and most of these things are the products of weathering of rocks. Okay, so these are things that are being brought in in low concentrations in rivers, and they're very soluble in seawater, so they can build up huge concentrations. Okay, which means because they've got huge concentrations in the oceans and their fluxes in are relatively small, that the residence time are very long. And we can have a look at some of these residence times now. Okay, so that the major ions in seawater, chlorine and sodium. Okay, so you see they're added by rivers. Okay, and their removal processes are also kind of relatively slow as well. They're removed by when seawater evaporates in some kind of like coastal regions, and also they're removed when seawater is actually subducted in subduction zones. Okay, so these are very, very slow processes. Okay, so the fluxes out are very small. Sodium and chlorine are really soluble ions, so they can build up large concentrations in the oceans, which means that their residence time is very, very long. Okay, but if we look at some of the other elements in this table, okay, so for instance calcium and magnesium, particularly calcium, these are elements which similarly have really high solubilities in the ocean. They have really, really low inputs in terms of their very low concentrations in river water, so we'd expect them to be quite high or have very long residence times, and they have residence times of the order of millions of years, but they're a lot shorter than sodium and chlorine because they have these additional output fluxes, so they're removed from the oceans at a faster rate, okay, and that's because they're involved in kind of like biology, so things build shells out of calcium, that increases the removal flux, okay, that leads to it having a shorter residence time. Okay, still millions of years, but it does mean that kind of on the timescales of millions of years, the concentration of calcium can change in the ocean, whereas on the timescale of millions of years, the concentrations of chlorine and sodium can't. It would take hundreds of millions of years for us to change the concentrations of chlorine and sodium. Okay, so what are the impacts of this? I mean, we need to think now about mixing in the ocean as well. Okay, so residence time is kind of the average amount of time any one particle would spend in the ocean. But the concept of mixing time is slightly different. So mixing time is the amount of time for kind of any one parcel of water to kind of move around the ocean and kind of return to kind of where it started from. Okay, so you could think of this as analogous if you're mixing kind of like a cup of tea and you add some milk. Okay, the mixing time of that cup of tea is the time that the milk is all evenly distributed from when you added it across the whole mug. Now in a cup of tea that doesn't take very long, but imagine if you kind of like added some red dye. Okay, if we added like an enormous tanker of red dye to the ocean, okay, it would take quite a long time for that dye to be mixed out over the whole ocean. Okay, so kind of there are estimates about how long this would take based on ocean models and also kind of natural traces that have been added to the ocean like radiocarbon, and it looks like the mixing time of the ocean is somewhere between kind of like a couple of thousands to maybe 10,000 years. Okay, so this means that if you've got a residence time that is longer than the mixing time, okay, that element's concentration will be evenly distributed around the ocean. Okay, and this is the kind of what we would expect in terms of a depth profile through the ocean. So this should really say kilometers down here, surface of the ocean up here. This is a profile you would get kind of anywhere in the ocean of an element that is got a long residence time. Because the mixing time of the ocean is shorter than its residence time, its concentration is kind of evened out over the whole ocean. So this kind of X here is kind of like, you know, a stand-in for the concentration of chlorine or the concentration of sodium. Okay, so everywhere in the ocean it would have kind of a uniform concentration. Okay, so we would call this a conservative element because it kind of behaves conservatively in the ocean, doesn't really change much. Now sometimes these are referred to as bioinert. Okay, and that's not strictly true in that biology does use, you know, some of these elements. It does use magnesium, it does use potassium. Okay, but the term bioinert kind of really means that the processes of biology are not acting in such a way to change the concentrations in the ocean. So biology isn't strong enough, kind of doesn't use enough of these elements up to change their concentrations in the ocean. Okay, and these are some examples of real measurements from the ocean. So the pink squares are measurements in a profile in the Atlantic Ocean, the blue in the Pacific Ocean. And you can see with depth, elements like potassium and chlorine here, they have relatively constant profiles with depth. Okay, so you can see some variability here, but if you make a note of the scales up here, we've zoomed in on where the variability is. If we plotted these from kind of 12 to 0 or 600 to 0, you would hardly be able to see any of this variation at all. Okay, and this variation that we're seeing here is not because the amount of chlorine or the amount of potassium is changing. Kind of really, you can think of it as these are concentrations because we're actually taking out or adding in water to these different parts of the ocean. So we're changing the overall salinity of the ocean. Okay, so if you imagine if you just added fresh water, okay, you would reduce the concentrations of all these elements. Okay, but the amount of these elements wouldn't change in the ocean. Okay, so the key thing is that if you look at these two profiles, they're exactly the same shape for chlorine, okay, and potassium in the Pacific and in the Atlantic. You see they're identical, and that leads to the kind of like a slightly better definition of a conservative element, in that conservative elements are defined by having element ratios that are constant with respect to other conservative elements. So for instance, potassium and chlorine are both conservative elements because the ratio of potassium to chlorine is the same everywhere in the ocean. Okay, so you could also look at the ratio of potassium to sodium or chlorine to sodium, and it would be the same everywhere in the ocean. Okay, and that's because the concentrations are only changed by the addition and removal of fresh water. Okay, so it's not just true here for the major ions, the ones that are really concentrated. So there are some also minor elements in the ocean which also behave in a similar conservative manner. Okay, so elements like uranium and cesium at the bottom here, they're present in much lower concentrations, okay, but they can still behave conservatively. They still have very long residence time, and this is because they have even smaller fluxes in and out of the ocean. Okay, so it's what determines whether something is conservative or not. It's not its concentration, but it's the ratio of its concentration into the ocean to the size of the fluxes in and out of the ocean. Okay, that's what's important. Okay, so now looking at some elements which are not conservative. Okay, so these are elements that have residence times that are of similar magnitudes or shorter than the mixing time of the ocean. Okay, so these are elements which kind of gets removed or added much faster compared to their contents or concentrations in the ocean. Okay, which means that the mixing of the ocean doesn't have time to even out all of the concentration kind of variability. Okay, so in the case of these elements, these are quite often the elements which are involved in biology. Okay, so elements like the nutrients like phosphorus, nitrogen and silicon here. And you can see here that they have quite short residence times because they're being removed actively by biological processes from the ocean. Okay, so in this we might see concentration profiles like this. We have depth going down here into the bottom of the ocean here, surface ocean up here, and you can see typically the surface ocean concentrations of biologically active elements are very low near the surface. Okay, that's because the concentration might be up here, but then any biology that happens uses up those nutrients, okay, and puts those elements into the organic matter. That organic matter forms particles which then sink down into the ocean and eventually break up and get respired back into dissolved phases, which leads to a reduction in the concentration at the surface and an increase at depth. Okay? So this means that we can get big differences both with depth and around the world spatially of these short residence time elements. Okay. And these are some real profiles of those. So elements like phosphate, or elements like phosphorus, which forms phosphate ions, which you can see here, or nitrate, which is made of nitrogen. So these are key nutrients in the ocean. So any biological activity that happens in the surface of the ocean, and biological activity happens at the surface of the ocean because that's where the light is. Okay, so photosynthesis requires light. So nutrients get used up in the surface ocean. Okay, they then sink down to depth. Okay, and they release those nutrients back into the water when the organic matter gets used up. Okay, so again, just like with conservative elements, it's not just the major elements; it's also kind of minor elements that are important for life, but they have short residence time, so they get used up in the surface ocean, like iron, barium. Okay, so these have non-conservative profiles. They have different concentrations, kind of in different places in the ocean, and that's key. Okay, so to summarise the kind of the nutrient. To summarise the residence time, we went over this concept of residence time. So it is the average amount of time any one particle kind of spends in the reservoir, okay? And you can define it for the total like water in that reservoir, but you can also define it in terms of stuff that's dissolved in that water. So the total kind of content of dissolved ions divided by the total fluxes of those dissolved ions. Okay, and the residence time is important because it determines whether there can be concentration variability within that reservoir. Okay, if it's very long residence time, you would have a conservative behaviour and the concentration would be uniform. And it would be very difficult to change the concentration. So if you change the fluxes, it would take a long time for the reservoirs to change its concentration. Whereas for bioactive or short residence time elements, okay, there can be variability in the concentration within that reservoir. And if you change the fluxes, it's very easy to change the concentration a lot quicker. Okay, so those are the key messages you should get from that.